All right. Well, thank you, Sam. That was a great introduction. It was not a real moose, by the way. It was fake for those watching online. So, hi, everyone. Thanks for being here and coming to listen. Thank you to Sam, Sander, and Charlie for organizing this. This has been absolutely amazing, like the best energy of any conference I've been to by far. So thank you guys so much. Yes, clap for them. And I'm honored to be here because there's so many people you've brought that I really respect. So it's like dream come true to be here and speak alongside them. So for those who I've not yet met, my name is Ryan Fleury. I work on the Rad Debugger, which is the project originally started by Rad Game Tools. You may have heard of it from like 2013 or whatever when it started, when I was like 15 or something. It's gone through some successive teams. But Rad Game Tools is now part of Epic Games. If it needs to be said, though, I'm not here to represent them. I'm here on my own behalf. So while working on the Rad Debugger, I've tried to prioritize something that I've always felt is missing from programming tooling, which is good visual feedback. So having open visibility into a system. I've always felt that computers are very opaque. Coming from game development, it's really easy to learn when you are always debugging things, that it's very useful. We saw in Dennis's talk that it's like if you're looking at timestamps, it's totally different experience than looking at a flame graph, right? It's a completely different experience. And game developers, you always are visualizing things. You're always trying to get a different view into your data to make something clear. And we use those visualization tools to create better software more efficiently, which is why we're all here, right? So, in other words, it's useful when cracking the code. I did the title thing, so. So there are many talks or resources on debuggers, but my impression is that not many of them focus on this visualization problem, even though I would claim it's perhaps the most important problem that a debugger needs to solve is quick, good visualization, flexible visualization into your data. So I'm going to present all the work that I've done on that problem to you all today. Now, if you aren't familiar with debuggers, or if you don't know what I mean by visualization using a debugger, I have some videos of the Rad Debugger that I'd like to share to set the stage for everything I'm going to talk about. So, first thing, if I've got my little game project, shameless plug. It's not really special yet, but if I've got this program, I can do things in the program. If I want to run that from within the debugger, in the case of Rad Debugger, I can do Rad Debugger, same command line. Opens up the debugger. I can either launch the program from, with the debugger attached. I can also step into the program. These are all very common debugger features, right? I can step through the code. So in that case, I'm stepping over lines of source code. I can evaluate things if I hover them. So if I can put a variable into the watch window here. So in this case, it's the global shared, and if I expand that, you can see as I step through the code, you see things change live. It's very, very common debugger features, really. Debuggers also tend to have features to navigate to different parts of the code. So I can go to some function and place a breakpoint, say stop at this line of source code, and so on, right? That's pretty basic debugger stuff. That's this is what it looks like to use one, right? Google Slides is weird with videos. Okay, so let's say I've got a crash in my game. I'm hooked up to my game. I hit F5, or I press the green arrow. F5 is hotkey for that. The debugger will catch that. It'll show me where that is. I can dig into things like the call stack. I can evaluate things still. I can see why some bug is happening, right? I can sort of get visibility into the system when something goes wrong. I can go back frames in the call stack, stuff like this. Okay. So, let's say in my game, for example, the player can hit something. So if I go ahead and spawn a little jelly entity here, I can walk up as the player and punch it. If I wanted to specifically stop when that punching code path is hitting, I can go ahead and find wherever I wrote the code, put a breakpoint there, and then I can just wait for that event to happen, right? Wait for that code path to be executed. You stop. And at that point, I can inspect the state, right? Most, very common debugger stuff, but I know a lot of people don't. They claim they don't use debuggers, so I figured I would just show it. You can also add conditions to a breakpoint. You can say, only stop if this condition is true. So in this case, I'm checking if it's specifically the player's right hand from our perspective, right? So yeah, there you go. So what exactly do I mean by visualization? As I kind of covered already, a basic version of this is the watch window, right? You can evaluate an expression and see things change. Another example would be memory view. There's just another very common visualization technique in a debugger. You just want to see a grid of bytes in sort of a hex editor style view. And then many of the same things apply, right? As I step through the program, I can see particular bytes change. So here I'm evaluating the string variable. And then I think I go to the memory for it, and if I step, you'll see it changes, etc. So basic, very common debugger visualization features, but this is the subject. Now, again, just a couple basic examples. We'll get into more later. But I find this particular problem important because for me, while learning programming, things would often feel like this. Now, for those who don't know what this is, I didn't either. This is the origin of the term black box. It's a flight log recording device, and yes, I thought it would have been black as well. But no, it's orange for whatever reason. But in programming, we've abstracted the term. As we know, programs can be understood as a transform from A to B, right? Some input data in some format A to some output data in format B. We use the term black box when we don't know anything about why something happens between A and B. We don't know why it produces B, we don't know how it's happening. We hit a button, we run a program, and something happens, out pops a B. Maybe you hope. If it works, great, and if it doesn't, God help us, right? Another way of looking at this is that the arrow in the middle, the code, is showing very few signs of life. Your program is doing something maybe undesirable, and you don't know why. There's very little information coming out of the system. Meanwhile, you just want your program to work. As I see it, the challenge here is that computers are inherently opaque to us. They're doing billions and billions of things per second, and so there's actually an enormous amount of information you might actually imagine needing in order to understand what's happening. So it's always a game of understanding how to narrow down to the subset of information you actually care about and presenting it in a way that makes sense. Now, one of the first ways we learn to extract information from a program is through textual logging or print debugging. Your program does whatever it was going to do, and then in addition to whatever it was going to do, like the thing you actually wanted it to do, it produces a parallel output, which is just like the textual log of what happens. They come from print statements you annotate your program with. Now, you'll see some people make the argument that this is all they need. And what I'm about to say might surprise you, but in one sense, they're right. But there are two problems with their argument. One problem we can solve while keeping print debugging, one problem we cannot. Problem number one. Text often sucks. It's often insufficient, right? You can't understand what it's actually encoding. Let's go ahead and do an example. Let's say we have some image format decoding, decoding code, and we want to test it, and we expect to get something like this image, right? Can anyone tell me where the bad pixels are after I've loaded the image? I've done the printf debugging. Okay. If you're looking at this, it's like, oh, like what's that? What are those fuchsia pixels in the corner, right? Like what is that about? So you can instantly see the problem when it's presented to you in a different way. Similarly, you have some 3D geometry data, and I give you this. You're not going to be very quick to like pick out where the broken vertex is, right? But if I show you this, it's like, wow, something's really off there, right? It's like you've got this cube structure, and then what's that vertex doing over there? Like, what is that about, So there are numerous examples like this. Text is sometimes exactly what you want. It's oftentimes not. But this is the problem I suggested we could solve. So even when text is not enough, you didn't necessarily need your log to just produce text. You didn't just need the print statement, right? Or maybe that's not the only thing you could have done. So this is an example of one solution to that problem. This is GraphViz, or a screenshot from the GraphViz visualizer. In this case, your program still outputs text, but it outputs text in a structured format that can be parsed by a visualizer program. Present your data like a graph like this, right? Another example, this is Mustache, made by Casey, who you all heard from yesterday, specifically designed to debug image and video compression software. So this system works pretty much the same way as print debugging, but it's structured, right? It's not just textual data. It's not presented as just textual data. In the same vein, there's this program called RenderDoc. Anyone who's done any amount of GPU programming probably knows that without this program, your life was probably pretty bad. Everyone has their story of you set up all this boilerplate, OpenGL, Vulkan code, whatever it is. You run your program, you're really excited, and there's a black screen. It's just what's going on, right? RenderDoc's extremely useful, so it sort of logs all the API calls you get, and it captures state, it hooks those APIs, and it captures that state, and presents it in this form. It knows the before and after states of every GPU resource that you touch when you make those API calls, right? Or caused by the work implied by those API calls. So it's another example, it's yet another structure of a structured, non-textual log. So just to be clear, I'm not saying that logging is wrong or not useful or can't be better than just helpless print debugging, but there's another problem. Problem number 2 is time, and thus money and sanity. The second major problem with log debugging is that it often requires modifications of the program that you're digging into. So let's set aside the cases where you can't actually do that, right? You're not doing any reverse engineering, you're not doing any of that. You can control your program, you can modify the program. There's still a problem with requiring that in order to get at very simple information. Let's walk through the series of steps you might go through when using logs in order to debug a black box. So first, you're presumably writing some code for some actual task you have. Number 2, you build, right? You wait for your build to complete. You run, create whatever state you wanted to be in to observe the code that you wrote, and then you check the log, right? You observe the log. And then a very common outcome of this process is you realize info you needed isn't logged, you add new logging code, and you go back up to the build step, and then you run and observe. Same thing with profiling, same thing with any form of logging is like this, right? Because it's explicitly wired into the program's code, right? In other words, let's say you're missing some expression x from the log, where x could be anything you might evaluate within a log or print statement. After you discover this, the new information you have that you could enter into the system is simply x. In a very basic, more ideal user flow, you would just have to write that. You just have to say x. X is what I'm looking for, right? Instead, you have to find a spot in your code, write the extra printing or logging code, and that's the best case, right? We don't know what it's going to look like. You build, you run and recreate whatever state you wanted to be in, and then you browse the log again. And needless to say, the huge problem with this is roughly instant for the user. This is often frustratingly long. So even in a small, well-organized code base that builds very quickly, that's optimized for very good development times, this will take many extra seconds. Furthermore, if a code base isn't prepared to recreate state very easily, which it very often is, not prepared to do that, it'll be much worse. And lastly, browsing the log itself can often be quite slow. And the reason why is that it's a fire hose of information, right? You have so much information pouring into you, and you're just looking for, sometimes the log is useful information, right? Sometimes you want to see it over time, but if you're trying to zoom in and really narrow in on one particular thing, you have a whole window of information that you have to look through. So, I think of this problem as being related to information flow. A constant cycle of information passing between the user and the computer. So you, on the left there, good diagram, pass down your information as inputs, computer returns it back out as outputs, right? So we repeat this cycle of information flow in order to sort of refine our data over time. It's this constant back and forth with the computer. You start with some very unrefined state, or no state at all, and then you progressively refine it. You build towards whatever you're trying to build towards. For programmers, the data we're working on is code. So if we zoom into one of those like little blob shapes, we've got A to B prime and then A to B double prime. That's what we're refining. The information flow cycle is sort of what pushes this forward, right? We see the outputs from one state, we produce information that encodes a new state, and so on and so forth. So we can think of this refinement process as like a repeating cycle across time. And now maybe this is all just like a little abstract, and I get it. But the reason I frame it this way is to associate certain problems on computers, like with programming or debugging, or understanding anything with certain undesirable properties of this sort of like wave pattern that you end up seeing. For instance, programming can feel very frustrating, or more opaque or more difficult to understand when this cycle has a much longer frequency. If the flow of information is blocked on something, let's just use compile times as an example. You tweak something, you accidentally touch a C++ header file, you're in like some major nightmare C++ code base, you hit build and you're like, great, I can't wait to test this new like jump speed or whatever, and it's like 10 minutes, just gone. That's an example of like deterioration of this information flow, the quality of this information flow, just due to this frequency expanding. So this is less efficient, it's less effective, it's not good. Furthermore, the information flow doesn't only have a frequency, but a bandwidth as well. Now, to be fair, I probably could have drawn that as like the amplitude, but I just wanted to make it like thick versus thin for whatever reason. I don't know, it's all abstract, but you get the point. If you're waiting a long time for some information to come back, it's better if you get a lot of information. If you get very little information and you're waiting a long time for it, it's like almost completely useless. So the goal is to maximize frequency and maximize useful bandwidth. So let's take a look at logging from this perspective. Logging does obviously have the ability to provide useful information. It can dramatically improve the bandwidth of information output from the computer back to you, but it can require many slow iterations to refine for some debugging case. And again, there's a universe of information you could be looking at. You can't log all of it. And it can also slow down the execution of the program itself. So you get a little bit thicker bandwidth, but you decrease the frequency a bit. So hopefully I've been convincing enough to show that while logs can be good and while this is a completely valid technique, it can be less efficient than what you might imagine is the ideal case. That's where a debugger comes into play. So I'll start by saying that I often see debuggers misunderstood. If I could have gone back in time, if I was in charge, I wouldn't have called them that probably. I mean, I understand it's like the physical bug in the machine. Everyone knows the story. But it might illuminate them a little bit today, like modern debuggers, if you think about them as just a program analyzer, so giving you a window into your program. Really, it's just giving you information extraction tools. In any case, a debugger allows us to analyze a program at runtime without modifying it. You can use structural information about the program stored in debug info to get like read eval print loop style features at the limit. And therefore, you shortcut the code modification process altogether. You completely avoid the tool chain. Importantly, a debugger allows us to avoid that second problem of modification time. How long does it take for me to get some new information out of the system, all right? So the reason I've been so focused on debugger visualization and the reason why I would argue it's important, and hopefully it's been convincing and justifies this talk. First, the visualizations don't need to be textual, and second, they don't need to require this build, run, recreate state, observe loop. So in order to be useful, a debugger has to meet that mandate. It needs to provide a variety of visualizations, not just textual ones, and it needs to be able to do it quickly. If it can't provide a variety, then it forces the programmer to go back to custom logging tools And if it can't do it quickly, it's faster anyways for the programmer to go back to the program and just write their own custom visualizer, right? So if it can't do both of those things, then the utility of a debugger dramatically drops. So let's look at how this will work. I'll start with a brief introduction to the basics of how debuggers work with your programs at all, and then we'll build up from there. First, let's consider how your program is executing on a modern operating system. And note that, like the terminology I use, it differs across environments or platforms, but you can find analogs of everything. It's all, you'll find the matching terms if you look. So when you start your program, you've got your executables file on disk. There's a bunch of DLL files on disk. Those can be referred to as executable images. When you launch your process, the kernel's loader is actually going to take those images and it produces modules. Modules aren't exactly the same as the executable images, but you can think of modules as sort of the loaded equivalent into your address space of those executable images. The process also includes a page table to map from, it's got a virtual address space. It maps from virtual addresses to physical addresses. And your process also contains one or more threads that are executing just pieces of code, right? And each one includes things like a register file. The kernel scheduler then is like, I've got all these threads, I'll start putting them onto these cores, we'll schedule them, get them going, and then your program is executing. Right? So a debugger is just a program, and so when it executes, it's just another process, one which the kernel records as being attached to got it, thanks. It's just another process, but the kernel is just recording the debugger as being attached to the debug. It's just a state in the kernel. When a debugger is attached to another process, which I refer to as the debuggy, I don't know if anyone else does that, but it's kind of, I don't know. Hopefully it's clear. Hopefully I don't fumble it. But point being, when you're attached as the debugger, the kernel will report to the debugger debug events. You get sort of a series of debug events. Sometimes the building blocks that the kernel provides are lower than this, but in principle, this is sort of how you can conceptualize it. And these debug events include things like, okay, a thread has been created, a module has been loaded, etc. Or, I should say, this one's important, or an exception has been hit, right? Like a hardware exception. So the debugger process control, like the piece of the debugger that's doing process control, and the debuggy are in kind of one of two states you can think of it. Either the debugger's process control is running and the debuggy is paused, or the debugger process control is paused and the debuggy is running. So kind of a ping pong between these two states is happening. And this means that execution between a debugger and debuggy can sort of be, you can think of it as interleaved across time. Like, it's mutually exclusive. Only one is really doing things at a time. This allows the debugger to sort of interleave its execution with the debuggy in a variety of ways. So this is how the runtime code modification actually works. It's that the debugger has the opportunity to sort of mutate the debuggy live before it continues, so you can change how it's actually executing. That's how it avoids the whole build step altogether. Now the granularity here is somewhat subtle, and it varies by platform. So, for example, while the debuggy is executing, the debugger could still be doing UI. Like, it's not necessarily exactly that, the entire debugger is stopped while the debuggy is running. Now on Windows, it tends to look a lot like this because it's explicitly like wait for a debug event API. So in that case, it's like your thread is literally sleeping here. So it looks a lot like this, but hopefully that's clear enough. So this interleaved execution, like I said, the debugger can do a bunch of things like read registers, write registers, read debug events or obtain debug events, read memory, write memory, and so on. And then, from that covers all of it, right? Read and write reading is the blue, and then writing is the orange, right? So we know that a debugger can read registers in memory, which is really the main building block for like extracting information out of a process, right? You can read memory, right? And so like all we need is to like ask the user for an address, ask them for a size, and then we just show them the bytes, and then we're done, right? Visualization, the end. Obviously not. As the user, you don't want to ask about address. What did I write? 0x1F43B5C00B0. You wanted to ask about X. And ideally, the system which allows you to ask about X is flexible enough such that X is a large set of expressions. It could be many things you could ask about your program. Debuggers know how to evaluate something like X through an expression evaluation system. And this is where all the visualization stuff starts kind of piecing together. So let's dig into that. Evaluating expressions, it's just a compiler. It's just a compiler problem, normal compiler problem. We know how to solve those. If we have some textual expression, like entity.targets at 5, the first step we can use to understand that expression is to parse it into a structured representation. Now, Sam has some opinions that will invalidate what I say, maybe, but the traditional pipeline is like, okay, first you're going to parse it into some sort of abstract syntax tree structure. In this case, not surprising, square brackets at the top, 5 on the right, dot operator on the left, entity dot targets for the children of the dot operator. From there, you can evaluate types for the abstract syntax tree. You can type check it, you can interpret it, or you can produce any intermediate representation that you need. You can lower down to bytecode. You could even lower down to native code. In this particular case, if we boil down to like a simple sort of stack machine, like intermediate representation bytecode like format, not that surprising. Push the address of entity, add the offset of targets, add 5 times the element size of whatever this array is, and then you pop, and that's your address of entity.targets at 5. And then, obviously, to compute the value of something, you just read from whatever that address is, because the debugger can do that, and then you've got your value. So the full pipeline might look something like this, and we can call that an evaluation. So you start with the text, you get an abstract syntax tree, you get an intermediate representation, a type pops out, and you get a value finally at the end. But how does our compiler know what the address of entity is? Like, what was that? And how do our compiler really wants to talk about the same things that the actual program compiler talked about. Like the thing you're interacting with when you write the code, the debugger wanted to talk about that stuff too. And we can do that with debug info, which is provided to us by the compiler and linker. Whoops. Okay. So debug info contains a ton of stuff. Like there's just tons of stuff in there. I'm not going to cover all of it. But you can think of it as sort of a serialization of what the compiler and linker did to turn your high-level source code into your final executable images, right? So it's sort of a recording of like what work happened, if that makes sense. So one thing that debug info has, which I don't cover here because it's not exactly relevant to this talk, is line information, which will take, it takes like ranges of executable code inside of your executable image, and it maps it to some source location. So that's like one thing it's used to implement things like stepping. Not going to get into that here, but that's in debug info too. So these are all of the parts that I would consider relevant for like evaluation, the basics of an evaluation system, right? So you've got types, globals, thread locals, procedures, location info, scopes, and locals. All this information about all of these is inside debug info. The thing about debug info, very cross-referential. So globals all point to their type information. So a global variable obviously has a type, global gets a type, thread locals get a type, procedures get a type, local variables obviously get a type. Locals refer to their location info, hint, for the address of entity thing, we'll get there. And scopes refer to the local variables that they contain, and the procedures refer to the scopes that are sort of nested under them. Zoom into types. Types take the form of a directed graph. So let's say I've got some type, int32, 4 bytes. Everyone knows what an int32 is here, I would imagine. The type information records that as sort of a basic type. It can encode like the name of it, and then its size, and then probably like it's just got a fixed code for this in pretty much every case. Types can also act as type operators on some other type. So you've got a type, it can point to another type and say I'm an operator on that type. So here, I've got this 16 array type, and it points at the N32 type, and if I point at the 16 array node, that's a 16 array of N32s. If I've got a pointer type pointing to the N32, if I point at that, if I say like that type, that's going to be an N32 pointer. Double pointer, 32 array of double pointer. Type information, maybe unsurprisingly, also covers user-defined types like structures. If I've got two structures here, and we've got entity, vec3, entity's got position, velocity, vec3, x, y, and z. Then there's some base type float32. You know, not that surprising, hopefully. Position points at vec3, velocity points at vec3, x, y, and z point to float32. That's how that'd be laid out. So, like I said, debug info has data about scopes in your program. So let's say I've got this procedure update. We've got some local variable, entity, pointer, entities, and we've got two loops. We've got some IDX variable. That's how I shorten index. I don't know how many people do that, but so index, and then we've got, maybe we're looping over the entities or whatever. So if we have this, then in debug info, you've got a procedure record for the update procedure. It points at a scope tree underneath which you also have local variables. So you've got, at the root scope, you've got the entities variable. At the two subscopes, you've got two different index variables. And each one of the variables points at their type info. So you've got index, maybe points to int64. Entities points to a pointer, which points to an entity type. That's how the type might show up. A variable like index not only refers to an int64, might also refer to its location information. And this location info is how our debugger's expression compiler can actually understand where certain variables live. So if our variable index within some scope is at like the value of the stack pointer, minus 64 bytes, then the location info is what's going to tell us that. It's going to encode that somehow. It might also tell us that a variable lives inside of a register, or the value of a variable is like, it could be arbitrarily complicated, really, that it can be computed somehow. But those cases tend to show up in optimized builds, right? You're not always going to have complicated cases like that. Global variables and thread locals tend to have much simpler location info. They tend to be like fixed offset, like address offsets into, in the case of globals, like a module or something. So with all of those pieces, we can sort of put together a compiler in the debugger which evaluates expressions. So now that we know how to compute the value of an expression, I'll unpack how we can begin to visualize it. So the most basic form of visualization that we can do for an evaluation is turn its value into a string, right? Just turn it into text. So, for example, you've got some entity expression. You want to turn it into a string like this. You've got, left curly brace, and then you print out all the members recursively, and so on. So what this code path does is sort of inherently dependent on the type information of some evaluation. So you can first note that we've got a set of like known simple cases, right? We know how to print an integer. We know how to print a floating point. We know how to print, strings are complicated. But we know how to print those two, right? It's like an integer. We know how to do that. Maybe we can change the radix. With floating point, also you can change the radix. But we know how to print these two things. With strings, it's relatively basic, but it's not as trivial as those first two cases, because strings, they're not normally encoded as, or they're normally encoded as like a pointer or an array of characters in the case of like C types. Obviously, there's formal types in the languages, but in terms of debug info, there's no string, like there's no formal string type in the debug info, obviously, because debug info evolved around sort of the C tool chain. There's the standard of string types in other languages, they're not buried that deep in the ecosystem. So if it's a pointer to a character type, it's a pretty safe bet that it's a string. But if it's a pointer to a U8, it's like maybe a string. Like who knows for sure, probably, maybe not, not really clear. But you can try it, and then if it doesn't produce any, seemingly readable text, maybe don't use it. The other caveat is that you don't actually know how many characters you're working with, right? You don't, because it's just pointers in the type info, you don't know that like that's what everyone talks about with pointers. You don't know how many things they're pointing to, so, you kind of have to guess. You could say, I've got some fixed upper limit. I'll look for a null terminator. The UI can only render so much text anyways, so you can have a pretty small limit, but, not too difficult. With enum values, you can just look at the enum type info since that's in the debug info. You can like try to find some member inside of the enum type info, see if an integer evaluation or you'd have it as an enum evaluation. You could say like, I've got this integer value. Let's try to look up at the enum type information, find out if there's a member inside of the enum that there's a member that has a value that matches whatever value I evaluated. Then I use the name. If not, then maybe I just fall back to the integer case or whatever. The only missing piece here are compound types like structs, unions, and arrays. So with a struct, might want something like that, like I mentioned earlier, braces, iterate the members. So this can be done by just, you walk basically the struct members recursively. So you walk to each child, and then when you come across another compound struct, you've got a struct inside of a struct. You've got to say, okay, I'm going to recursively descend into that. So I go, doesn't have to be literally recursive, but the sort of algorithm is sort of recursive. You need like a stack. So yeah, you walk the children, you do that. You can get a string like that. With arrays, very similar problem. You've got some, you have some notion of how many elements are in the array. So you can say, well, I found the base address of the array, but to actually visualize this as a string, I want to go, okay, go to the first element, turn it into a string. Second element, turn it into a string. Commas delimiting them. Pretty basic problem. This is also recursive. So what I want to note here is that both of these exhibit sort of a single pattern that we can think of, which is that if we've got some evaluation, you've computed some evaluation, certain types can produce a set of child evaluations, right? So in the case of the struct, you produce all the members, and if, in the case of arrays, you produce all of the array elements. Another common case, just before I move on, pointers don't always point to strings. Obviously, like sometimes they point to a struct. In those cases, you don't just want to see like, oh, my pointer value is like that. It's like you want to see what it's pointing to often, other than struct memory. So in that case, that's also another case of expansion. You just dereference the pointer. That's your child evaluation, basically. And then you actually do the recursive path. So if you're pointing at an integer, you print the integer. If you're pointing at the array, you print the array. So on and so forth. It's just one layer of indirection removed, right? So that gives us all the building blocks we need, actually, to build a very simple watch window. You input expressions, and then you just stringify them. They've got type info. You could write a very simple stringification path, if you will, for the type. There you go. That gives you a watch window. But a very useful property of a watch window is not only that you can enter an expression, but that you can also expand them. So this is really useful because, more often than not, like that single line visualization path, it's like you've got 256 elements in an array or whatever, and you only see the first 8. You don't want to be like, okay, now evaluate array plus 8, and then array plus 16, and array plus 32. It's like a whole nightmare, right? Same thing with structs, especially, you don't want to force the user to like think of like, oh, like what was the fifth element of entity? Like, let me put that in as